Let's talk about 1905. It might not sound like a particularly special year, but in the world of science, it was an earthquake. It's the story of one man working a pretty normal day job who, in his spare time, published a few papers that didn't just tweak physics, they completely rewrote the rule book for reality itself. This is the story of Albert Einstein's Annus Mirabilis, his miracle year.
And you know, it all started with simple thoughts, just like this one. Not in a fancy university lab with all sorts of equipment, but in an office, reviewing patent applications. This one little thought experiment about falling, which he later called the happiest thought of my life, it really shows you how his mind worked, seeing these huge cosmic truths in everyday situations.
And believe me, that new way of seeing things was desperately needed. See, back in 1905, physicists kind of thought they had everything figured out. They were feeling pretty good about themselves. But just beneath the surface, some really deep cracks were starting to show. Puzzles that the old-school classical science just had no answer for. And the person who was about to fix these cracks? Well, it wasn't some famous professor at a big university. It was this guy, Albert Einstein, a 26-year-old patent examiner. I mean, look at this contrast. His official title was Technical Expert Third Class. His bread-and-butter job was looking at patents for things like gravel sorters. But in his free time, oh, you know, he was just completely overhauling our ideas of light, matter, space, and time. An absolute explosion of genius.
So, what were these big problems? Well, physicists at the time had a name for them. They called them the clouds that were ruining their perfectly sunny view of the universe. First, there was this really bizarre thing light did called the photoelectric effect. Second, everyone was looking for this invisible stuff called the luminiferous ether that was supposed to fill all of space, but no one could find it. And third, a really basic question still wasn't settled. Were atoms even real?
All right, so let's see how Einstein starts blowing these clouds away. His first two papers of 1905 didn't just offer little suggestions. No, they were radical, game-changing solutions for the very nature of light and matter themselves. Okay, first up, the photoelectric effect. Here's the deal. Scientists knew that if you shine light on a piece of metal, you can knock some electrons loose. But here's the part that drove them crazy. A faint beam of blue light could do it, but a super bright, intense beam of red light did absolutely nothing. It was the color, the frequency, that mattered, not the brightness. And according to the physics of the day, that made zero sense.
Yeah, this is the big question, right? I mean, if light is a wave, like an ocean wave, then a bigger, brighter wave should have more power. It should hit harder. But that's not what the experiments were showing. It meant that something was fundamentally wrong with how they were thinking about light.
Einstein's solution was just beautiful and totally out of left field. He said, hey, what if light isn't a continuous wave at all? What if it's actually made of tiny, individual packets of energy? He called them light quanta. We call them photons today. So think of it like this. One packet of light hits one electron and gives it all its energy. A brighter light just means more packets, but the energy of each packet only depends on its color. Blue packets have more punch than red ones. And just like that, the mystery was solved.
And you have to understand, this wasn't just a clever fix. This was the birth of a whole new kind of science, quantum theory. It was so radical, so groundbreaking, that even though he published 4 legendary papers that year, it was for this one idea, explaining the photoelectric effect, that he eventually won the Nobel Prize.
But don't think everyone just stood up and applauded. This idea was so weird that a top American physicist, Robert Millikan, spent years doing super precise experiments just to prove Einstein's reckless hypothesis was wrong. And here's the best part. His own meticulous data ended up confirming Einstein's idea perfectly. Talk about a beautiful irony. Okay, one crisis down, but Einstein was just getting warmed up. He immediately turned to another one of those clouds. For a long time, scientists had talked about atoms, but for many, it was just a useful concept, not something that was actually real. There was no direct proof.
The clue was something called Brownian motion. You've probably seen it. It's that random, jittery dance that tiny particles like dust or pollen do when they're in water. Well, Einstein did the math and showed that this random zigzagging was actually being caused by something, the constant, invisible bumping and shoving from individual water molecules. His paper gave scientists a way to actually calculate the size of these invisible atoms. It was the smoking gun. Finally, atoms were undeniably real.
2 papers down, 2 to go. So he's redefined light and he's proved atoms exist. What could possibly be next? Oh, nothing much, just the very fabric of space, time, and energy. This was the deepest, most troubling problem in all of physics. Basically, you had one set of rules for how things move, Newton's laws, and another set of rules for light and electricity, Maxwell's equations, and they just didn't agree with each other. To try and patch it up, scientists invented this mysterious, invisible substance called the ether that was supposed to fill all of space. But every single experiment to find this ether had failed.
Einstein's approach was just pure genius. He basically took a broom and swept the whole complicated mess, including the ether, right into the trash. He started over with just two simple, elegant ideas. First, the laws of physics are the same for everybody, as long as you're not accelerating. Makes sense. But the second one, this one breaks your brain. He said the speed of light is constant. For everyone, it doesn't matter if you're flying towards a light beam or away from it, you'll always measure its speed as the exact same number.
The consequences of that one rule are just wild. Because if the speed of light is the one thing that can't change, then something else has to. And that something else is space and time. It turns out, for things moving really, really fast, time literally slows down, and space gets squished. They're not separate, absolute things. They're woven together into a single, flexible fabric, space-time.
So this complete upheaval of space and time naturally led to another huge question. If our most basic ideas were wrong, what about mass and energy? Are they really two different things like everyone always thought?
Well, in a short little follow-up paper, almost like an afterthought, Einstein dropped the answer. It would become the most famous equation in the entire world. So what does it actually mean? It means that mass and energy aren't separate at all. They're basically the same stuff, just in different forms. Mass is just a super concentrated form of energy. They're two sides of the very same cosmic coin. You can convert one into the other. And the real key to all this is that c² part. C, the speed of light, is already a massive number. When you square it, it becomes an astronomically huge number. And that means that even a tiny, teeny bit of mass can be converted into a staggering, almost unbelievable amount of energy. This is the secret behind everything from nuclear power to the atom bomb. Okay, so let's just step back and take a breath. 4 papers, 1 year. The very foundations of physics had been completely reshaped. What is the lasting legacy of this incredible burst of creativity? Well, here's the wild part. In 1905, Einstein didn't just start one revolution in physics, he started 2. His paper on light quanta kicked off quantum theory, the weird, probabilistic physics of the very, very small. And his paper on special relativity kicked off the other revolution, the physics of the very, very large, governed by the smooth, predictable geometry of spacetime.
And that brings us to the ultimate legacy of 1905. These two magnificent theories, both born from the same mind in the same year, are fundamentally incompatible. They just don't work together. So, in solving the biggest problems of his time, Einstein accidentally created the biggest challenge for every physicist who came after him. How do you unite his two masterpieces?
Which leaves us with this final, thrilling question. That journey that started in a Swiss patent office is still going on today in giant particle colliders and on supercomputer screens all over the world. The search for a single, unified theory, a theory of everything, that can finally bring Einstein's two great conflicting ideas together and give us one complete picture of reality.